Hi folks, welcome to part one of the implicit differentiation lesson. So I'll talk a little bit about what that even means later on. Let's take a look at the first question here. So we're considering a car moving on a circular track, and they're telling us that the track can be modeled by this equation. Hopefully you recognize this as representing a circle centered at 0, 0 with a radius of square root of 10. Now it tells us that if a car were to skid off the track, it would follow the path of the tangent to the circle. All right, and then they want us to determine the equation of that tangent at these 2 points. Now, I think this is something that you're probably aware of, but let's do a little experiment here. That if I've got a car moving around in a circle, or any object moving around in a circle, okay, that if at some point I take my finger out, okay, so that would cause, like in the problem, the car to skid off the track, it's not going to keep moving around in a circle. Okay, I'm pretty sure everybody knows that when I let this go, okay, where did it go? It went off in a straight line. And that straight line is the line that's exactly tangent to the circle. Okay, so given that we're working with a scenario where the tangent to a curve is important, it makes sense that calculus is going to come into play. All right, so let's draw this circle, okay. So here's our circle with a radius of root 10. All right, and what they want to do is they want us to find the equation of the tangent at position 1, 3. So right about there, and negative root 5, negative root 5. So that'll be on this portion of the circle. All right, so again, if this car is moving around, say counterclockwise, if it skids off or loses control at this point, it's going to follow the tangent to the curve. Of course, if it's traveling clockwise, it'll just move, it'll go off in that direction. All right, but either way, the equation, this line, will describe the motion of the car when it skids off at that point. Okay, now that sort of makes sense, because remember what the tangent line represents. The tangent line represents the best approximation to the curve at that point. So at this very moment, the car is moving in that direction. All right, this line here represents the behavior of that function in a small neighborhood of that point. Okay, and similarly here. So if we want to find the equation of the tangent line, well, we're going to need the slope and we're going to need a point. So we already have a point. We know that they're going to share the point 1, 3. So we have to find the slope of the tangent, which of course we're going to find using the derivative. Okay, now what's different about this function is that it's not given as a function of y explicitly in terms of x. Okay, so just note my use of the word explicit here. Okay, we say that this relation, since it's not technically a function, this relation is defined implicitly because the y variable is just mixed in together with the other terms. So it's not explicitly written as y equals some expression in x. But of course, if we want to use our calculus methods, we're going to have to do that. So our first step is to take this relation and rewrite it by isolating y. Okay. Now, of course, when we take the derivative, when we take the square root of both sides, we have to keep in mind that we can have both the positive and negative square root. All right, and this actually makes sense if you think back to what you might have done back in grade 10, and you realize that the positive square root of 10 minus x squared really just represents the top half of this circle, and then the negative square root represents the bottom half of the circle. So given that it's a relation, it makes sense that you actually need two different functions to define this particular relation. All right, so if I want to find the slope of the tangent at 1, 3, I realize I'm going to have to work with the positive square root. But when I find the slope of the tangent at negative root 5, negative root 5, I'm actually going to have to use the negative square root. Okay, so that's one issue that we're seeing here. So first of all, we had to isolate for y, and then we realized that we're having to deal with two different functions. So we realized that if I had just said, find the slope of the tangent at x equals 1, which is what we normally ask when we're working with functions defined explicitly, you wouldn't have to be told what the y values. You could just calculate it. But here we see that at x equals 1, there's two different y values that are going to have two different tangents. So we're starting to see that working with these relations is going to be a little more complex. But let's do this here. So let's find y prime. So again, I'm working with the positive square root, so I'm just going to apply the chain rule here. So it's just 1/2 10 minus x squared to the negative 1/2 times the derivative of 10 minus x squared, which is negative 2x. Okay, so if we want to find y prime at 1, okay, actually let's simplify this here. So let's replace x by 1. So here we just have negative 1 over 10 minus 1 squared, which is just going to be 9. Square root of 9 is 3. So the slope is just negative 1/3. So again, it makes sense that the slope is negative based on our diagram. Okay, but if I want to find the slope at negative root 5, okay, I have to use the other function, the bottom half. Okay. Now, I won't, again, if we take the derivative, I'm going to see that I don't really have to do too much work. The only thing that changes is I'm going to have this extra negative in front. So negative, and the rest is going to be exactly the same. All right, and in fact, here, the negatives cancel out. And 2's reduce, so all I'm left with again is just x over square root of 10 minus x squared. And so when I plug in negative root 5 into this here, what do we have? We have negative root 5 over square root of 10 minus negative root 5 squared. And of course, this is just going to be equal to 5. 10 minus 5 is 5, root 5. So I'm just going to have negative root 5 over root 5. So negative 1. All right. So again, this problem's certainly doable. Now I'll actually do the equation later on, okay, because they actually ask us for the equation of the tangent. But for now, I'm just sticking with determining the slope of the tangent. So now we have enough information to determine the equation of the tangent here, because we have the point on the slope, and similarly for this point here. Okay, so I've already talked about a couple of the issues that come up. So issue number 1 is solving for y. Now, in this case here, solving for y, wasn't that difficult, really, okay? But once I did it, I had to work with two different functions and then figure out which one I was going to use in each scenario. Again, not too difficult, given that I was able to draw it on a graph very easily, so I knew which portion represented which function represented which portion of the graph. But imagine we have a much more complex function where solving for y takes a lot more work. Or we're going to see some examples where you're given a relation that's defined implicitly where it's actually impossible to solve for y. So this scenario where we were able to use our traditional methods just won't work at all, because there will be no way to solve for y in terms of x. Okay, so this gives us an idea that maybe we're going to have to consider something else. And this is where we're looking at option 2. Instead of isolating y, we're just going to take the relation as is, and we're just going to differentiate both sides with respect to x. Now, as we're doing this, you might see some relationships to what we did with determining the derivative of a logarithmic function, or determining the derivative using logarithmic differentiation. That was, in fact, an application of what we're going to be doing here. All right, so let's just take this equation, x squared plus y squared equals 10. And let's just do what they tell us to do. Take the derivative of both sides with respect to x. Now you say, why? Because in the end, remember what I'm looking for. I'm looking for the slope of the tangent. And in other words, I'm still looking for the derivative of y with respect to x. Okay, so let me just take the derivative of both sides with respect to x and see what happens. Now we notice that the right-hand side is nice and easy because the derivative of a constant is just 0. All right, so that's a good thing. And here I've got the derivative of a sum, so that's just going to be the sum of the individual derivatives. So it's just going to be the derivative of x squared with respect to x plus the derivative of y squared with respect to x equal to 0. All right, this is nice and easy, just equal to 2x. This is where things get a little dicey. because I'm taking the derivative of y squared, which is, an easy enough expression, but I'm taking it with respect to x, okay? And so this is where the hint comes in about using the chain rule, all right? And so remember that y is related to the variable x. We just don't have it given explicitly. Okay, so this y here is going to be like my u. So what's the derivative of u squared with respect to u? Well, it's just 2u, or 2, in this case here, y, times the derivative of u with respect to x. Remember, u is just that y value. So in other words, the derivative of y with respect to x. But this is exactly the expression that we're looking for. So again, similar to what we did with logarithmic differentiation, is we don't take the derivative of y directly, but it ends up coming out as a product of this process of just differentiating both sides. All right? And hence, this is why we call this process implicit differentiation. Okay? You can think of this as explicit differentiation, where you have a function of y in terms of x, and you're just taking the derivative of that function. Here, you're just taking the derivative of both sides of this implicit equation, and out of that comes out the derivative of y with respect to x. So now it's just a matter of solving for that. So dy dx is equal to, I'll bring the 2x to the other side, negative 2x, and then here divide by my 2y, and let's simplify that. So the derivative of y with respect to x is just equal to negative x over y. All right? Now, we sort of took a lot of steps to do this. We kind of did it very carefully, but you realize that this was quite easy to do. No worries about square roots or anything like that. But I hope you notice that something very different happened. This is the first time we're seeing this, where the derivative itself includes not just x variables, but also expressions with y, okay? And this is one of the big differences that we'll see when we're using implicit differentiation, is that our derivative itself contains the variable y in it. Okay, and this also kind of makes sense when you think about the fact that they didn't just give us an x value as to where we were finding the tangents, they also gave us the y value. Okay, now what's nice about that is that if you look at what we have here, it doesn't matter whether I'm working with the top half or the bottom half of the circle. This formula works for any point on the graph. Okay. However, again, what you do need is the y value. So let's see if we get the same answer as before. So I'm going to show you a bit of notation here, because when we're finding the derivative at a particular value, well, you can just input an x value. Okay, because remember, this is a derivative function. Here, when you're differentiating implicitly, you actually have to input both the x and y values. So we're going to use this notation here. We're going to use this bar, and then at the bottom is where you put your inputs, your y value and your x value and your y value, that point. So what this represents is the derivative of y with respect to x evaluated at the point 1, 3. Okay. Here, because y prime was given as a function of x, I could just use the traditional notation. All right? And by the way, this is notation you will see in other parts of calculus. So let's see what we have. We have negative 1 over 3, and lo and behold, the exact same answers we had before. All right? And when we find the derivative of y with respect to x evaluated at negative root 5, what do we get? Well, negative, and x is equal to negative root 5, okay, over y is equal to negative root 5, okay, and we see these negatives cancel out, the root 5s cancel out, and what am I left with? Just negative 1. Exactly what we got earlier. All right? So, again, in this particular problem, is using this idea of implicit differentiation necessary? No. But what it does is, with this easy example, we start to see how one might use implicit differentiation when one can't solve for y explicitly. And that's what we'll see in the next example. All right? So just to recap before we find the equations of these tangents, okay, instead of isolating for y, what we do is we just take the equation as is with y implicitly included in the equation, and you just take the derivative with respect to x of both sides. You use your derivative rules, including the chain rule, when you have an expression that might have a y value in there, and then you just solve for dy dx, which is exactly that thing that you're looking for. All right, and then from there, given the point, you can determine the slope of the tangent. So now, to find the equations, that's nice and easy because I could just take my slope, okay, take my slope, take my point, put into y equals mx plus b, or even better, use good old point slope form, okay? So if you didn't watch that video, you just have to take my word for it. You can do it using y equals mx plus b, no problem at all, but I'm going to use point slope form. So point slope form says that I take y minus the y value of my point. So in this case here, it'll just be 3. And that's going to be equal to the slope, negative 1/3 times x minus the x value of my point. And there you go. There's the equation of the line. Now, if you wanted to put it in slope-intercept form, you could just distribute. Sometimes people prefer putting that 3 on the other side. So writing it as negative 1/3 x minus 1 plus 3. Either one of these is acceptable. Okay, this is probably the nicer one because y is explicitly given. Okay, so that's my first answer. And then my second answer is just going to be y minus the y value here. So it's going to be y plus root 5 equals negative 1 times x minus the x value. So x plus root 5 again. And then I can give my final answer as negative x plus root 5 minus root 5. And there's my other answer. All right. So in the next examples, we're going to see how implicit differentiation doesn't just become, a novelty that we could use. It actually becomes something essential. All right. That's it for this one.